Hi, this is Professor Pradyot from Leadib Academy. We are looking into the video solutions for IBDP Chemistry HL Paper 2, May 2019. Okay, and I have given the paper reference number. Now, interestingly, we are not just discussing just the video solution, but more importantly, we are understanding the underlying concepts. Okay, so that it is more some kind of a revision to understand those basic concepts. Okay, and you will get the idea how the questions are being framed, what are the underlying concepts, so that there is a more clarity. Okay, so we at Leadib Academy try to bring the conceptual kind of a knowledge, understanding, and interestingly, we are providing the detailed courses. So if you need to know any specific topic, any specific subject in detail, you can very well subscribe to our courses, which we are uploaded on our website, leadibacademy.com. So please do visit. Okay, now let's start looking into the question number 4A. The stable, okay, rhenium Re was the last element with single isotope to be isolated. So the question is, the stable isotope of rhenium contains 110 neutrons. State the nuclear symbol notation in this form. So first understand, get just the concept that whenever it is, okay, let me remove this. Okay, so whenever any element is written like this, it should be clear. This is just the reminder. Okay, this represents the atomic mass number, and this is indicating the proton number or atomic number, or sometimes it is called just the atomic number. Okay, so what is atomic mass number? Very, very simple. It simply means the number of protons plus neutrons. Okay, P plus N. And obviously proton number means just the protons. Okay, I'm using a shortcut. So in case of rhenium, they have already given us that there are 110 neutrons. Okay, 110 neutrons. What about protons? No problem. We can refer to the data booklet. Okay, and you will find under the number of elements, you will find its atomic number is indicated as 75. So 110, these are neutrons, these are protons, that is nothing but the atomic number. So that gives us 185. Okay, and this we will write at just the 75. So in short, the rhenium will be indicated like Re 75 185. Very, very straightforward. Okay, at the bottom we write the proton number. Okay, we mention the number of protons, or many times it can be same as number of electrons, provided it's a neutral atom, it is not the ion. And on the A part, okay, upper one, we write it number of protons plus number of neutrons. Very, very simple. Okay, hope this is quite clear. Okay, next question 4B. Before its isolation, scientists predicted the existence of rhenium and some of its properties. Suggest the basis of these predictions. Okay, so they are asking, before it was isolated, rhenium, still the scientists were aware of the rhenium. Probably not the name, but definitely with its properties. So what is the basis? Okay, so important. Okay, let me put it like this. Okay, this is the modern periodic table, okay, which you people are already aware of. So when the founder or a father of modern periodic table, the founder, or we can say the inventor of the periodic table, is our Mr. Russian scientist Mendeleev. Okay, so when he constructed the periodic table, okay, he started coming out with this idea of arranging whatever the elements which were in existence that time. Okay, he could predict that, okay, if you observe very carefully, in the manganese, okay, these two elements, they were left with the gap. Okay, that is techtium and rhenium. Okay, these two elements, they were not present. That means there was a gap. He had left the gap. And what was the reason? Because the thing was basically that as per the modern periodic table, or as a periodic table concept, this table has been constructed, okay, with the fundamental concept that in the group, okay, we are talking about this, in a group, the physical as well as the chemical properties are more or less same, or there is some trend. It means that based on the manganese, it was predicted that there needs to be, okay, there needs to be, so what is important is that he had predicted, because in each group there is the chemical properties and physical properties, they are more or less same. Okay, and it was arranged as per the atomic number. So he could envisage that there is a gap at these two, and so he could predict that these two elements exist. Okay, so the basis is very, very important basis, that, okay, that periodic table is arranged, okay, according to properties, okay, chemical properties. So it means in the same group, okay, the elements with these similar chemical properties will exist. So that's the reason that, okay, let me clear this. That means the rhenium is under the same group, okay, same group, okay, of manganese. Okay, so it is falling under the group of manganese. So it is called manganese, and this is called Ika manganese. Okay, this element, which, and Re. Okay, Ika means in Sanskrit one, and Dvi means two. Okay, that means it is like a second kind of a manganese. Okay, these are in Sanskrit, okay, Indian language. So that is the basis. So the reason simple, that in a group, same chemical properties, and it has been arranged according to the atomic numbers, and the properties get periodically, they keep on coming. Okay, it's like a time period. Okay, after certain atomic numbers, again you will get the same property. If you observe very carefully, very, very simple, that 25 you add 18, you will get 43. Okay, That means this is going to have, then you add 32, okay, you will get rhenium, etc. Okay, that is the logic. So after certain atomic numbers, the same property element appears. That is the basis. Okay, and so based on that, it was predicted. Okay, very, very interesting one. Hope this is quite clear. Okay, 4B2. A scientist wants to investigate the catalytic properties of a thin layer of rhenium metal on a graphite surface. Describe an electrochemical process to produce a layer of rhenium on graphite. Okay, so simple. Okay, let's take a graphite electrode. Okay, this is the graphite electrode, and connect. Okay. Okay, we don't care. This is the graphite electrode, and then let's put the salt of rhenium. Okay, rhenium. So let's say rhenium chloride. Okay, rhenium chloride. Then what will happen? Okay, rhenium. Okay, it will get electrolyzed and it will travel to the cathode, and we will start getting deposition of rhenium. Simple. Okay, it is like Re2 plus ions are getting deposited on cathode. This is basically a cathode. Okay, and we start getting a layer. So what reaction is taking place? ReCl2. So we are getting Re2 plus and 2Cl minus. So we are interested in this. So this will get reduced to form Re. Okay, and this is what exactly will start getting deposited. So what we have done, we have carried out electrolysis of molten ReCl2, okay, rhenium chloride, and then during this on cathode, Re will get deposited, reduction. Okay, that's all. So very, very simple. We'll get the layer of rhenium on the graphite electrode. Simple. Okay, very, very simple. Let's look into the next question, 4B3. Predict two other chemical properties you would expect rhenium to have given its position in the periodic table. Okay. So we have been asked to predict, okay, its properties. So let's try and understand what kind of properties we can expect. Okay, given its position. Okay. So rhenium is basically in the group of manganese. Okay, rhenium is here It is very much. So rhenium is D block and transition element. So what kind of a properties we can expect? First of all, important property, variable oxidation states. Okay. It means it can exhibit +2, +3, etc. Okay, these are the variable oxidation. It is not like fixed, like let's say a group 1 or group 2, like alkali metal or alkaline earth metals or maybe halogens. Okay, it can exhibit basically variable oxidation. Then second property, it can form complex ions. Okay, we have seen that, okay, in the complex ions. Okay, that means these are coordinate compounds. Coordinate compounds. Reason, again, because there are a lot of empty d orbitals. In d orbitals, it can accommodate 10 electrons. There are 5 orbitals. So because of this high number of orbitals, if there are empty, so they can accommodate the lone pairs of electron. Okay, that is basically the theory behind coordinate compounds. Then another d block elements are this one, that they form colored compounds. Okay, and we have seen that why it can form colored compound, because colored compounds are typically because of the transition of electrons. Okay, and then another one, it will be paramagnetic, similar to manganese. Okay, and please remember, we have covered this in detail, d block element properties, okay, in our courses. So please do visit our website and subscribe to our courses, because we are covering all the important subjects of IBDP like chemistry, physics, math, etc. Okay, so please do visit so that you will have a deeper understanding, okay, of all this. But hope this is clear. Okay, even though they had asked us to indicate only 2 properties, but here we are described around 4. Okay. So quite simple. Interesting question 4C. Describe how the relative reactivity of rhenium compared to silver, zinc, and copper can be established using pieces of rhenium and solution of these metals. Okay. So first understand what is being asked. Okay. And let's say there is a rhenium plate. Okay. This is rhenium. And now we have been given solutions of, let's say, a silver. Let's say this is the silver sulfate. AgSO4 solution. What does it mean? It means that there are Ag plus ions and SO4 2 minus. Please remember, solution means it's typically ionic solution. Okay, so there are ions. Now understand a very, very important aspect. Suppose rhenium is more reactive, okay, Okay, if Re rhenium is more reactive then it will displace the specific metal. Okay, so what does it mean? Suppose rhenium is more reactive as compared to Ag. So what is going to happen? That Ag ions will get reduced on rhenium, okay, and they will start getting deposited. Simple. This is the logic. If rhenium is more reactive as compared to silver, okay, the silver will preferentially get reduced, okay, on the rhenium. That's all. Okay, that is the logic. And it simply means that the metals, so what would be the conclusion? Metals getting deposited on rhenium, okay, rhenium will be less reactive with reference to that given metal. Simple. Okay, sorry, what I mean to say, with reference to rhenium. Okay, so in short, metals which are getting deposited, for example, I'm showing, okay, assume that silver sulfate solution is there and silver ions are getting deposited, okay, on rhenium. Okay, they start getting deposited like this, okay, like this. It simply means that they are less reactive, that metal silver is less reactive as compared to rhenium. If they don't get deposited, that means they are more reactive as compared to rhenium. So that is the test, whether rhenium can displace that metal ions. That means whether it can take out those ions preferentially. That is the test. Okay, this is more like a displacing. Simple. Okay, so that you can test for rhenium, okay, zinc, sorry, you can test it for silver, zinc and copper. So whatever metals which are getting deposited, they are going to be less reactive. Extremely simple but very fundamental concept, okay, in testing the reactivity from the solution. Okay, 4D1. One chloride of rhenium has an empirical formula of ReCl3. And they are asking us to write down its IUPAC, okay, IUPAC name. Simple. What is the logic? Chlorine will always have a -1, so that means this is total is -3. That means rhenium will have an oxidation state or oxidation number of +3. That means we can say this is rhenium. Write down in the Roman numerals chloride. Simple. Very, very simple. Typically, when transition elements can exist in the variable oxidation states or oxidation numbers, so it is a practice to mention which chloride. Okay, so that's why it has to be written in the brackets so that we'll come to know that we are referring to the +3, because it can be +2 also, or it can be +5 also, etc. So just by looking at the bracket, okay, so that we can differentiate various chlorides or various oxidation state compounds. For example, manganese, it can exist from +2 to +7. Then which one we are referring to? So that we can make out easily by looking at this name. Okay, whatever is mentioned in the bracket, that indicates, this part is indicating the oxidation state. Okay, very simple point. 42, calculate the percentage by mass of rhenium in rhenium chloride. Okay, so how to calculate? Simple. First calculate molecular mass of ReCl3. How to calculate that? Take the atomic mass, okay, from the section 6 of the data booklet. Okay. So in this case, we can find out from the data booklet that atomic mass is 186.21 of rhenium. This is for rhenium. And for chlorine, there are 3 atoms. Each one is having 35.45. This is for chlorine. So by doing this calculation, we will get 292.56. Okay, and now we have to calculate mass percentage, okay, or percentage by mass of Re in ReCl3. Straightforward, we will divide 186.21, that is the contribution of Re, divided by total 292.56, multiply by 100 for converting into the percentage. And the answer will be, you can use your calci to find out this. Extremely simple. Okay, this is extremely simple calculation, percentage by mass. 4E, rhenium forms salts containing the perrenate, that is a oxidation state 7 ion ReO4 minus. Suggest why the existence of salts containing an ion with this formula could be predicted. Refer to the section 6 of the data booklet. Okay, so first let's get confirmed that is it correct. Okay, that is a ReO4 minus. Okay, so ReO4 minus, assume oxidation state. We know how to calculate. Oxidation state of rhenium in this case is X. Oxygen, we know always it is majority of the time it is -2, and there are 4 atoms, and overall the charge on this ion is -1. So we can easily see that X is equal to +7. So what does it mean? That means oxidation number of rhenium is +7 in this specific perrenate ion. Okay, that's the logic. Now how we can conclude that yes, it is matching with whatever it is predicted from the periodic table. So let's check from our tool, that is the data booklet or periodic table. Okay, so let me show, this is the section 6 of the data booklet. So where is our favorite rhenium? So rhenium, how to trace? it is basically falling. It's a manganese. So it is here. And what is the group number? Straightforward, it is a group number 7. Group number 7, that means we can easily conclude it can exhibit +7. And that's why we have seen that manganese also exists, okay? It does exist like MnO4, very famous KMnO4. Manganese also exists in this MnO4, permanganate, okay, +7. So easily we can see that looking at the group number, okay, it can exhibit this +7 oxidation state. Okay, so that is how we can conclude. Okay. Very simple, and that means it is matching with whatever the results we are getting. So even if we would have looked only at the data booklet, we could have predicted that yes, there is a strong possibility that it will exist as a +7. Okay, hope this is quite clear. Okay. Very interesting one. For E2, deduce the coefficients required to complete the half reaction. So it is just the balancing. So let's see, okay, how we can approach. So we can clearly see that oxygen on the left-hand side, there are 4 oxygens, and on the left-hand side, this is fixed. Okay, that means there is no scope for uranium, this OH, this complex. So it simply means that we have to put compulsorily 2 oxygens, okay, so that oxygens are balanced. So it simply means that now we have got 6 hydrogens on the right hand side, 2 into 2, 4 for water, and plus ReOH 2. Okay, so that means 6. So automatically this becomes 6. Now let's see. Now we need to balance the charge. On the right hand side, there is a total charge of +2. Okay, now we need to have the same +2 charge on the other side. Okay, left hand side. So how to take care of this? So 6H plus, it means that to get the +2, we have to add 3 electrons. Okay, now let's see whether everything is getting matched. Charge is getting matched. Yes, oxygen, rhenium, everything is getting matched. Simple. Okay, so this is how you do the balancing. Okay, simple. For E3, predict giving a reason whether the reduction of ReO4 minus to ReOH twice 2 minus would oxidize Fe2 plus to Fe3 plus in aqueous solution. Use section 24 of the data booklet. Appears to be very, very interesting and conceptual question. Very good question. Okay, so let me find out from the data booklet. Okay, section 24. It indicates me this. Okay, so what does it indicates? That the reduction of Fe3 plus to Fe2 plus, the reduction potential, okay, so this is what we call standard reduction potential, okay, that is 0.77 volts. Okay, and always remember that typically all the reactions, okay, these are redox reactions, they are being shown only as a reduction, okay, while explaining this standard reduction potential. They are always shown as a standard reduction potential, not as oxidation. So if we want to see that whether Fe2 plus getting oxidized to Fe3 plus electron, then we need to mention only this. We need to reverse the sign. Okay. And what is the mean by minus sign? Minus sign indicates that Fe2 plus is not very happy to get oxidized to Fe3 plus. Okay, it is not very happy. It means it prefers to stay in Fe3 plus, while Fe3 plus prefers to get reduced and get converted into Fe2 plus. Okay, it is like that. While Fe2 plus doesn't like to get oxidized. Okay, that is the logic. Okay, so anyways, so now the question is being asked, okay, that if we set up, okay, so let me give the idea that what we are talking about. Okay, so the question is that if we set up, okay, ReOH twice, okay, I'm just giving for showing it just for indication purpose so that you will get the concept right. And here it is Fe2 plus. Okay, and if we set up this cell, is it going to be spontaneous? Okay, this is the cell what I have formed. ReOH twice, okay, would oxidize this. Okay, that is a question. So what we need to do, this will be definitely anode because it has to get oxidized. So this is the anode and this is the cathode. Okay, and if we set up a cell, okay, whether there is a flow of electron, that means electrons need to flow from anode, okay, to cathode. Okay, so that is the question. So let's try to understand this. So already we have seen that ReO4, okay, ReO4 minus getting reduced. Okay, I'm just showing in short. We are already seen in the previous question. Getting reduced to ReOH2, okay, 2 plus. The E naught is indicated as plus 0.36 volts. Okay, so this is reduction. That means this is the cathode. Okay, very simple. So we are already been given this 0.36. So we will say this is E naught cathode, which is equal to plus 0.36 volt. Then how much is the E naught anode? Just now we have seen this is E naught anode. That is equal to minus 0.77 volts. Okay. Now what we do, basically we just calculate, okay, the E naught of cell. So how we calculate E naught of cell? E naught of cathode plus E naught of anode. In this case, so 0.36 volts minus 0.77, so it will give minus 0.4 volts. Okay, this is going to be the E naught of cell. If we set up like this, that means ReOH twice is acting like a cathode and Fe2 plus is acting like anode. So what is the implication of this? It simply means that this cell will not be spontaneous. Will not be spontaneous. Okay, it means that, okay, it simply means, therefore we can conclude reduction of ReO4 minus will not oxidize Fe3 plus. Okay, it is simple. Fe2 plus. It is as simple as that. Reduction of ReO4 minus, which is taking place, okay, at cathode. Oh, I have shown wrongly. Sorry, it's my mistake. I should be showing like this. Okay, sorry. I should be showing like this. ReO4 minus. Sorry. Okay. So it is very, very simple. So reduction of ReO4 minus will not oxidize Fe2 plus, which we want. Okay. Very, very simple. Okay. So the concept is that find out, you set up a cell and check whether you are getting a positive potential. It means the reaction is going to be spontaneous. So what is mean by that? That means whatever the EMF is being set up, that means the electrons which are getting released from the anode will reach the cathode and they will reduce, the reduction will take place. Oxidation always takes place at anode and electrons are being driven through the circuit, okay, in the external circuit, and they will reach the cathode, and in cathode reduction will take place. Okay, that is the technique. So in this case, since the E cell is negative, this is not going to be possible. Okay, this is not possible. This reaction will not be spontaneous and it will not be. Okay. Very simple concept if we understand this concept in a deeper manner. Okay. Hope this is quite clear. Very interesting question. Very good question. Okay.